In this example, we'll just compute some order, so we'll be computing order modulo some number. Let's take the current year, 2020. And the number, let's take something we have to take which is co-prime to the number 2020, and the factors of these are 2 and 5, and we can take 3. That will be invertible and will have a well-defined order. So the task is to find this order. The approach I'll use is to factor the modulus into the product of powers of primes, and that would involve 2 some number of times and 5. So the 5 will be squared, and the 2 will appear okay, better do it in steps. So okay, no, I'm not saying it right. It's not just 2 and 5. Will be something else left. Interesting. So let's take 20 out, and then what will be left is 101, and 5 will not appear in a square because inside the 20, which is here, is only one copy of 5, but 2 will appear as a square. So the prime factors in the decomposition of 2020 are 2, 5, and 101, and 2 appears twice. So by the Chinese remainder theorem, computing this order is the same as computing the least common multiple of the orders modulo 4, modulo 5, and modulo 101. So I need to know them, and then I will know my answer. Well, the first, the order modulo 4 of 3, by the definition, is the smallest power of 3, which is equal to 1. I can guess it without even computing, because it's supposed to divide the earliest function of 4, which is 2. Well, I'm computing something, and then only 2 divisors, 1 and 2. And 1 is not good for the order because the first power of 3 is not 1, so 1 is to be discarded, and we have the answer 2. And of course we can check it. 3 squared is congruent to 1 mod 4. And the next computation will be modulo 5 of the same number 3. So we need to find the order modulo 5 of 3, the smallest power of 3, which is congruent to 1 mod 5. The possibilities are divisors of the earliest function of 5, which is 4. And now we have 3 divisors, 1 and 2 and 4. And of course 1 is not an option, 3 is not congruent to 1 mod 5. The square of 3 is 9, it's also not an option. Let me record that. Is 9, which is mod 5, which is negative 1. And that has to be discarded, which leaves us with 4. And of course it is true that the 4th power, which we can write as the square of the square, is the square of negative 1, which is 1. So that is now the smallest power of 3, which is congruent to 1 mod 5. What is left is to find the order modulo 101. So again, I could start by listing possibilities. They are all divisors of the earliest function of 101. Since 101 is a prime, the earliest function is 100, and the divisors now are very numerous. It's 1, 2, 4, 5, 10, 20, 25, 50, and finally 100. So these are possible divisors. One is of course not an option, I just listed as a divisor, but it is not an option, and so is 2, and so is any power of 3 which is less than 101. And yes, the first power will be 5, which is bigger than 101. So the power 4 is also not an option, but let's compute it anyway, so that we will have access to the fifth power. So the fourth power is of course the square of the square, which is the square of 9, which is 81. And modulo 101, I can replace it by negative 20, which is easier to work with. So when I will be computing the fifth power, I'll be multiplying 3 by this, and that is negative 60 modulo 101, and that is still not congruent to 1, so 5 is not an answer, is not the right answer. And let's proceed to the next in line of divisors. So we can skip 6 and 7 and 8 and all that, because they are not going to work. And the 10th power we can compute as the 5th power squared. So that would mean taking the square of negative 60, which is as good as the square of 60. So that will be on those 3600. But I'm working modulo 101, so I can take multiples out. So I can take 3030 out, which will leave me with 570, and I can reduce it by 505, and I will be left with 65. And 65 I can bring down to the next differentials, and here subtracting it from 101, or rather subtracting 101 from this, and ending up with negative 36. I like it better. So still not congruent to 1. 10 is not our answer. Let's compute the 20th power, which will be the squares of the 10th power, and will be congruent to the square of, say, negative 36. And some cheating maybe is in order. I don't want to compute the square of 36. I just fear that I make some mistakes. Instead, I will just break it into product of things and compute their squares, and then reduce them, if necessary, modulo 101. So well, it's really basically computing yeah, okay, let's see. So 36 is the square of 6, and 6 itself is a product of 2 and 3. So I have the fourth power of 2 and the fourth power of 3, and minus sign disappears in the square. So the fourth power of 2 is in the range of remainders. It's actually quite a small number. It's 4 squared. It is 16. The fourth power of 3 is in the range of remainders, but we can replace it by negative 20. So that is a certain reduction, which makes the computation easier, because that only knows the product of the two will be negative what is it, 320, and that we can change by adding multiple of 101, which is 303, and that will bring us down to negative 17. So I will just stop here. What is essentially this step is not it is not 1 congruent to, so that means that 20 is not an answer. And I have to check now the power 25. So what I can do with the power 25, I can write it as a product of the 20th power and the 5th power, which I already have computed. So that will be negative 17 for the 20th power and negative 60 for the 5th power. And so I just need to multiply the two. And the result will be with plus. So that will be 600 plus 420, so that will be 1020. And that can be reduced by taking 1010 out, which is a multiple of my modulus. And what will be the remainder of that is just 10. Again, not congruent to 1, that is not the answer. The next in line is the 50th power, which I can write as the square of this, of the 25th power. Because 10 is a very nice number to compute with, so that will be congruent to the square of 10, which is 100. And that is as good as negative 1. So I'm still not seeing 1, this is not the answer, but that is the only option I have, and that is the right answer, because now if I compute the 100th power, I'll be computing the square of this, which is as good as negative 1. So negative 1 squared is going to give me 1, and that is the first power of 3, which is 1. So now I know all the orders which I need to combine in the least common multiple fashion. It's 2, 4, and 100, and of course this common multiple is just this 100. This is the largest possible order modular 2020, and that's the order of our number 3. So that is it for this example. See you later.